Are you ready? Are you ready? Let's build real futures together.
You know, usually when we talk about enterprise infrastructure, there is this explicit expectation of structural integrity.
Right, absolutely.
Like, think about engineering a physical skyscraper. You dig deep into the earth, you pour these massive concrete foundations, you bolt the heavy steel framework together.
Yeah, and the architect just points at the blueprint and confidently says, that will hold 100 stories.
Exactly. It will withstand a hurricane. You can look at it and know exactly what its limits are.
Because physical architecture is mathematical. I mean, it is absolute. Bedrock is bedrock. And we fundamentally like our enterprise systems to be held the exact same way.
We want them visible and meticulously categorized.
Right, entirely predictable. When you build a solid foundation, you just expect it to hold the weight.
But then you step into the world of enterprise data analytics. You step into massive business intelligence deployments, and suddenly that solid concrete foundation starts looking, well, a bit like a swamp.
That is unfortunately very true.
We are looking at a structural landscape that is honestly incredibly fragile if you do not know exactly what you were doing beneath the surface. I mean, you can build the most beautiful, interactive, cutting-edge dashboard on the top floor.
But if the underlying data pipeline is compromised, the whole thing is just a house of cards.
Exactly. The entire structure collapses under the weight of a single complex query.
It is the absolute definition of architectural quicksand. And the stakes here are incredibly high.
Which brings us to our mission today. Welcome to this Cortex Lab Masterclass deep dive. We are entirely focused on navigating that quicksand.
And we are operating under the assumption that you, listening right now, already know your way around the basics.
Yeah, no hand-holding today. We
No.
are not here to explain the mechanics of a bar chart.
Right. We are definitely not going to walk you through dragging and dropping a visual onto a canvas. You are already way beyond that.
Our mission today is to elevate you from building, amateur departmental data models to adopting the uncompromising, rigorous mindset of an enterprise data architect.
We are dissecting massive data pipelines, semantic modeling strategies, and high concurrency architecture.
We are pulling insights from a really advanced stack of sources for this deep dive. We've got technical manuals, deep dive excerpts from Jack Hyman's foundational texts.
And some incredibly dense translated transcripts from expert data science panels.
Yeah, and the overarching theme across all of these sources is a massive transition. It's moving from the passive world of manual reporting to the realm of proactive, automated business intelligence.
The sources actually point out a fascinating contrast that kind of frames this entire discussion.
Right, the spreadsheet dinosaur analogy.
Yes, standard legacy spreadsheets, which, by the way, many multi-billion-dollar organizations still inexplicably rely on for critical operations, are essentially dinosaurs.
They struggle with anything beyond basic rows and columns.
Exactly. They lack any real relational intelligence.
But the platform we're exploring today, specifically the Microsoft Power BI Enterprise ecosystem, is built for the next generation of true intelligence. I mean, it can ingest millions of records from over 100 different data source types simultaneously.
Which is incredible. But that immense processing power is exactly the hook.
Because with that much capability comes a terrifying risk.
Right.
Catastrophic system latency.
Oh, absolutely. If you do not build the architecture perfectly, you are going to bring your servers to their knees.
You will have C-suite executives staring at a spinning loading wheel for 5 minutes just to see yesterday's sales figures.
And in an enterprise environment, a slow dashboard is a dead dashboard.
Completely useless. So to prevent that, we have to start at the absolute bedrock of the system. Let's unpack the enterprise architect mindset and the strict data lifecycle.
So the foundation of any enterprise business intelligence deployment revolves around a very strict 5-stage lifecycle.
Prepare, model, visualize, analyze, and manage.
Right. And universally, across all our advanced sources, the preparation stage is recognized as the most tedious.
Definitely the most unglamorous.
Yeah, easily the most critical. It dictates the success or failure of the entire ecosystem.
Okay, let's unpack this. Because I want to look at why this preparation stage is where the amateur approach violently clashes with the enterprise architect's approach.
It's a fundamental difference in philosophy.
We have all seen it. An amateur developer spots a data anomaly, maybe a mismatched formatting issue or a redundant category.
Or a null value that is just completely throwing off a metric.
Right, and instead of fixing it at the source, They try to fix it at the dashboard level.
Which is madness.
They write some incredibly complex, convoluted front-end DAX workaround to hide the dirty data from the user.
Which is the architectural equivalent of putting a fresh coat of high-gloss paint over black mold in your living room.
Wow, that is a great analogy.
I mean, it looks fine for a week, but it does absolutely nothing to solve the underlying structural decay.
And senior enterprise architects take a fundamentally different approach.
They prioritize relentlessly clean data modeling at the ingestion layer. They understand that a poorly prepared data set inevitably results in faulty visualizations.
Sluggish performance, and ultimately disastrous business decisions.
It's like baking a cake. You cannot bake a premium cake with uncleaned, raw, disorganized ingredients. The heavy lift of ingestion must be done in the desktop authoring tool, not in the cloud service.
But I have to push back here, or at least play devil's advocate for a moment.
Okay, go for it.
I have a hard time believing senior teams do not know this. Everyone pays lip service to clean data. So why do so many highly paid senior data teams still fail at this preparation stage?
That is the million-dollar question.
Is it just laziness? Or is it the pressure of tight, agile sprints where the business stakeholders are demanding immediate visual results so the developers just take the path of least resistance?
Well, if we connect this to the bigger picture, it is not just laziness. It is a fundamental lack of what software engineers call separation of concerns.
Okay, an architectural failure.
Exactly. Many teams, even senior ones, treat this massive enterprise platform like it's just a larger version of a spreadsheet.
They try to do everything everywhere.
Yes. They try to perform data transformation in the analytical layer, and they try to perform analysis in the presentation layer. They blur the lines between where data is shaped and where data is evaluated.
So they lack discipline in the data pipeline.
Completely. The heavy lift of ingestion, the cleaning, the sorting, the transformation, that must be done in the engine room.
Not in the cloud service where the final product is consumed.
Right. And to execute that separation of concerns perfectly, an architect must master the first major battleground of the data ecosystem.
The ETL engine. Extract, transform, load.
Exactly. We are talking about the strict division between the two programming languages operating under the hood here, the M language and DAX.
This is where we see the most critical architectural decisions being made. M and DAX are not interchangeable.
Not at all. They have completely different architectural mandates, different evaluation engines, and different syntax rules.
Right. So Power Query utilizes the M language. M stands for mashup. It is a functional, highly case-sensitive language designed explicitly to pre-process, clean, and transform data before it ever enters the relational model.
It is the gatekeeper.
Yeah.
M shapes the landing zone.
And yet, this is where we see the most common fundamental preparation pitfalls that derail entire enterprise deployments.
There is actually a specific section in our sources detailing what 99% of experts get wrong during this M phase.
Let's get into that.
Mistake number one is the misguided attempt to create what we call a megatable.
Oh, the dreaded megatable.
Yeah.
I want to spend some time on this because it is such a pervasive habit.
It really is.
Developers think they are doing the system a favor by flattening everything out. They take their customers, their products, their dates, and their sales transactions, and they merge them all together in M to create one massive flat sheet.
Because they think, well, if everything is in one table, the system doesn't have to do any complex relational joins, so it will be faster.
Right. But in a columnar database ecosystem, that is a fatal error.
It is a profound misunderstanding of how the underlying Vertipack storage engine actually works. Vertipack does not read rows like a traditional SQL database. It reads columns.
So when you flatten your data into a megatable, you basically destroy the engine's ability to compress the data efficiently.
Exactly. You make the data incredibly difficult to manage, and worse, you ruin the analytical engine's ability to filter contextually across different dimensions.
And that leads directly to the second major mistake we see all the time, allowing mismatched data types between related columns.
Oh, that's a nightmare.
If you have a primary key formatted as a text string in one table and the corresponding foreign key formatted as a whole number in another, the model relationships will fail entirely.
The joins just will not execute. The architecture shatters at the structural level.
Because the Vertipack engine cannot implicitly convert those types during a relationship evaluation without a massive performance penalty.
Which brings us to perhaps the most critical advanced framework in the ETL battleground, and a concept that truly separates the amateurs from the true enterprise architects: query folding.
Yes. For you listening, if you are not obsessing over query folding in your M scripts, you are leaving massive, easily attainable performance gains on the table.
You are actively harming your server infrastructure.
Let's really break down the mechanics of this. Wait, so query folding is essentially the M engine being lazy, right?
I love that analogy.
It's writing a SQL query, handing it back to the massive source server, and basically saying, hey, you have way more compute power than I do. You do the math, apply these filters, drop these columns, and just give me the final answer.
That is an excellent way to conceptualize it. It is the ultimate delegation. Query folding is a mechanism where the M mashup engine evaluates the transformation steps you have built.
Things like filtering rows, renaming columns, grouping data, or merging tables.
Right. And instead of downloading millions of raw rows and doing that heavy lifting locally in memory on the Power BI gateway, it translates your M steps into native query statements, typically SQL.
And then pushes that SQL query all the way back to the original relational database server.
Exactly. It forces the massive multi-million-dollar SQL Server cluster to do the processing, returning only the perfectly clean, lightweight, highly compressed dataset over the network.
It saves incredible amounts of bandwidth and memory.
But the sources highlight a massive edge case here that catches a lot of developers off guard.
Query folding can break.
Yes. And when it breaks silently and disastrously. It is very fragile.
So if a developer applies a specific transformation step in M that the source database does not natively understand, say, a complex custom text extraction or a specific index generation, the query folding chain just snaps.
Or using a function like table buffer, which explicitly forces the data into memory.
Precisely. The moment the folding chain breaks, the M engine gives up on delegation.
It just throws its hands up.
It issues a basic select star query to the database, downloads the entire massive raw dataset across the network, and then attempts to process the remaining transformation steps locally in the gateway's RAM.
Which is catastrophic at scale. If you are dealing with a table of 200 million rows and you break query folding on step 3 of a 20-step process, you are going to cause massive network congestion, memory timeouts, and system latency.
I have a genuine question about this, though.
Sure.
I look at this from the outside and wonder, if query folding is so fundamentally important to the health of the system, why isn't it just an automatic default that cannot be turned off?
That is a fair point.
Why does the M engine even allow developers to break the fold? Why not just restrict the M language to only functions that translate to native SQL?
Well, this raises an important question about the philosophy of the tool itself.
Hmm.
Power BI is designed to connect to over 100 different data sources.
Right, it's not just SQL.
It connects to SQL Server, yes, but it also connects to flat CSV files, web APIs, SharePoint lists, and legacy OData feeds. Those systems do not have native query engines. They do not speak SQL.
Ah, so M has to be the universal translator.
Exactly. The M language has to be flexible enough to mash up data from a beautifully indexed SQL database and a messy, unstructured JSON file at the exact same time.
So the burden of optimization is placed entirely on the architect.
You have to know when to fold and how to sequence your steps to maintain that fold for as long as possible before hitting a non-foldable transformation.
Here is where it gets really interesting for me. If the M language is so incredibly powerful at the database level, and it can leverage query folding to push all this work back to the server, why don't developers just do all the mathematical calculations in M?
I see where you're going with this.
Why not calculate your profit margins, your year-to-date sales, your moving averages right there in the M script before the data even hits the analytical model?
That is a very common trap for developers migrating from traditional SQL reporting backgrounds. They try to pre-calculate everything.
Because that's what they're used to.
Right. But M is strictly for structuring the landing zone. It is entirely static. It shapes the physical tables during the scheduled refresh window.
Ah. But enterprise business intelligence requires dynamic, on-the-fly mathematical context.
Exactly. Because the user dictates the context at runtime. When an executive clicks a specific product category on a matrix visual and then cross-filters it by clicking a specific region on a map visual, the calculations need to instantly recalculate based on that exact, highly specific new filter context.
And M cannot do that. M prepares the structure, but it cannot respond to user interactions.
For that dynamic context, we require an entirely different evaluation engine, which is DAX.
And this transition from the static preparation of M to the dynamic evaluation of DAX relies entirely on the physical architecture that sits between them.
Right. Once the data is transformed and loaded by M, the way you structure the physical tables dictates whether your complex DAX queries render in 3 milliseconds or 3 agonizing minutes.
Which means we need to talk about the physical shape of that landing zone. We know what a star schema is.
The gold standard.
If you are listening to this, you understand the basic concept of a central fact table surrounded by descriptive dimension tables. We are not going to insult your intelligence by explaining what a sales amount is versus a product name.
But what we do need to dive into is the Vertipack engine. Why does the Vertipack engine absolutely hate wide, poorly structured fact tables?
What is actually happening at the silicon level when hundreds of enterprise users hit the system simultaneously?
To understand that, we have to look at how column interstorage engines compress data. Traditional row-based SQL databases store data row by row on the disk. Vertipack stores data column by column,
Okay.
and it utilizes several aggressive compression algorithms, the most important of which is dictionary encoding.
Let's break down dictionary encoding. Because once you grasp this, the entire concept of star schema optimization finally clicks.
It really is the key.
Imagine you have a column in your fact table for payment method, and you have 50 million rows of transactions. In a legacy system, the text string credit card is literally written out and stored to the disk millions of times.
Which is incredibly bloated, but Vertipack does not do that.
Right. Vertipack scans that entire column of 50 million rows and builds a tiny, lightweight dictionary.
It sees there are only maybe 4 unique values: credit card, debit card, cash, and wire transfer.
And it assigns an integer to each. Credit card becomes 1, debit card becomes 2, cash becomes 3.
So it replaces the massive text strings in the actual 50 million row column with just a sequence of tiny integers.
And computers can process and compress arrays of simple integers with terrifying speed.
Exactly. This is why the architectural mandate for fact tables is to make them extremely narrow and numeric.
But this is also where we see massive pitfalls that destroy model stability in high concurrency environments.
Yes. Developers often violate the star schema by introducing high cardinality primary keys directly into the fact table.
High cardinality meaning a massive number of unique, distinct values. The classic example that ruins models every single day is the transaction ID or receipt number.
Oh, absolutely. If you have a fact table with 50 million sales records, and you include the literal transaction ID string in that table,
You now have a column with 50 million completely unique text strings.
and the dictionary encoding completely fails. The engine tries to build a dictionary, but the dictionary is literally 15 million entries long. It is as big as the table itself.
So the compression ratio drops to 0. The model size bloats exponentially on the disk, and when the server tries to load that model into RAM to serve your hundreds of concurrent users, it consumes all available memory.
The system thrashes, and performance is completely destroyed.
Which is why the uncompromising mandate here is the KISS principle. Keep it simple, simple. Enterprise architects must ruthlessly prune their models.
They use features like choose columns during the M phase to permanently delete any fields that are not strictly, absolutely required for aggregations or final visuals.
Put yourself in the architect's shoes right now. You are in a steering committee meeting. The business stakeholders from marketing or finance are looking at your data model proposal, and they say, well, we don't technically need the individual alphanumeric transaction ID for our aggregations right now, but we might need it later for a very specific line item audit.
The classic just-in-case argument.
Exactly. Just leave it in the model. Storage is cheap, right? How does an architect push back on that? How do you enforce the KISS principle without sounding obstructionist or unhelpful?
You have to reframe the conversation away from storage costs and entirely toward system latency and user experience.
Make it about their pain.
Right. Bringing in just-in-case data is the ultimate enemy of performance. Every single unused row, every single high cardinality column is a permanent, ongoing tax on the system's memory and CPU cache.
So you tell the stakeholders, I can include this granular audit data in the primary model, but it will increase the loading time of your morning summary dashboards by 45 seconds for every user in the building.
And suddenly, when you frame it as a daily 45-second tax on their time, they realize they do not actually need that audit data sitting in RAM.
It is about protecting the ecosystem. Pruning those columns is a huge part of the latency battle, but the other part of that battle is how the system physically connects to and accesses the data source itself.
We have to evaluate semantic modeling strategies and the profound architectural trade-offs between storage modes.
When we talk about enterprise scale, the choice between import mode and direct query is one of the most consequential decisions an architect will make.
Without a doubt.
Let me throw an analogy at you to see if this captures the fundamental difference. Tell me if this tracks. Import mode is like having a massive pre-prepared buffet right inside the dining room.
Okay, I like this.
The data is fully imported, highly compressed by the VertiPaq engine, and stored in memory within the Power BI cache. When a user queries a visual, the response is blazing fast because the food is sitting right there, ready to eat.
Right.
But the downside is the food might be a few hours old, depending on your scheduled refresh times. It is not up to the second fresh.
That is an excellent analogy. Import mode provides unparalleled analytical speed. The VertiPaq engine is optimized specifically for this.
But the sources reveal a massive tension when we hit the limits of enterprise scale.
Yes. Import mode is fantastic until you hit a database that is simply too massive to cache,
Right.
say terabytes of historical telemetry data, or when the business absolutely demands up to the second real-time data for operational monitoring.
And that is when developers immediately reach for direct query.
Naturally.
If import mode is a buffet, direct query is like ordering fresh from the restaurant kitchen every single time you want a bite. It offers a live connection to the source.
It leaves the massive dataset in the original SQL database and simply sends DAX queries, translated into SQL, back and forth in real time.
But UT, and this is a massive warning flag in the source material, direct query is severely limited.
Extremely limited. When you use direct query, you strip all the performance control away from the Power BI VertiPaq engine. You are now entirely at the mercy of network latency, gateway bandwidth, and the specific performance tuning of the underlying source server.
So if that SQL server is poorly indexed, your Power BI dashboard will be agonizingly slow, and there is nothing the Power BI developer can do about it.
Not only that, but direct query significantly restricts the complexity of the DAX formulas you can write.
Because the DAX engine has to translate your formula into the native SQL language of the source database?
Exactly. Any DAX function that doesn't have a direct SQL equivalent will either fail or perform terribly. Functions like time intelligence become incredibly risky.
This raises an important question about the architectural trap of direct query. Many organizations demand real-time data simply because it sounds impressive, without realizing the devastating performance costs they are incurring.
So what does this all mean for the listener? Are we saying that direct query is effectively a trap?
Is it just a false promise of real-time data that ultimately ruins the user experience because the waiter is constantly running back and forth to the kitchen?
Well, direct query should not be feared, but it must be applied surgically. It is an architectural decision that should only be made when live data is an absolute non-negotiable business mandate.
Like monitoring manufacturing assembly lines or active trading floors.
Precisely. Situations where the freshness of the data justifies the massive performance cost. If yesterday's data, or even an hour ago's data, is sufficient for decision-making, import mode is vastly superior.
But what if you need both? What if you have a massive historical data set, say 10 years of global retail transactions, that is physically too big to import into RAM?
But you still need fast performance for your high-level executive dashboards.
Right, while simultaneously needing the ability to drill down into the granular receipt-level details. This is where we get to the truly advanced framework. This is the masterclass level.
This is where we override the import is best rule by deploying composite models and user-defined aggregations.
This is a hallmark of true elite enterprise architecture.
A composite model allows you to combine import mode and direct query tables within the exact same semantic model.
Let's explain how aggregations work in this context, because it is essentially a magic trick of data engineering.
It really feels like magic. Aggregating data means summarizing massive, highly granular data sets at a higher dimensional level.
So instead of loading billions of individual transaction rows into memory, you create a summarized table that groups the total sales by date, by product category, and by region.
By doing this, you shrink the table sizes dramatically. A billion-row transaction table might condense down to a few thousand rows in the aggregation table.
You import that tiny aggregation table into memory for blazing fast performance.
Then you configure the model's mapping so the engine understands that the aggregated table is a perfect summary of the massive direct query table.
And this is where the magic happens. You create a highly responsive imported cache for 95% of user queries.
When the CEO looks at a high-level dashboard showing total sales by region for the quarter, the DAX engine intercepts that query and says, I do not need to send an expensive direct query to the SQL Server for this. I can answer this instantly using the imported aggregation table.
And the dashboard renders in milliseconds.
But, and this is the crucial part, if a regional manager clicks on that visual and wants to drill down into the highly specific individual transaction details for a particular store on a particular day,
The engine seamlessly and invisibly switches from the in-memory import cache to the direct query connection.
yes, it sends a highly filtered, very specific query back to the SQL database to fetch just those few specific rows.
It is the ultimate best of both worlds scenario. Zero latency for the high-level metrics, with the capacity to access infinite historical detail when necessary, all without blowing up the memory limits of the server.
With the structural architecture optimized, the schema pruned, the cardinality managed, the storage modes perfectly balanced, we finally turn to the analytical engine itself.
The engine that drives the actual business intelligence insights? We need to talk about DAX and what the sources call the complete blueprint to 100 out of 100 mastery.
DAX, Data Analysis Expressions. It is the advanced formula language.
It is what we use to create sophisticated dynamic metrics when the standard out-of-the-box sum and average features fail to provide the necessary analytical depth.
And the sources provide a very clear, uncompromising blueprint for memory management here. The ultimate unbreakable rule for optimizing the model's memory footprint is this: always prefer explicit measures over calculated columns.
The architectural difference between a calculated column and a measure is profound, and misunderstanding this is the #1 cause of model bloat.
Let's illustrate this difference physically. Let's talk about what happens during a scheduled data refresh.
Okay. When you write a calculated column, say, a formula that calculates the profit margin for every single row in your 50 million row sales table, that column evaluates row by row during the data refresh process.
Yes, it physically computes the value for row 1, row 2, all the way to row 50 million. And then, this is the critical part, it permanently stores those 50 million new values in the Vertipack engine's memory.
It adds physical bulk to the model. It increases the file size, it increases the RAM required to host the model, and it slows down the entire system.
It's like buying a heavy physical encyclopedia, a massive multi-volume set, and storing it permanently in the middle of your living room, just so you have the ability to occasionally look up one specific fact.
It takes up physical space constantly. Measures, on the other hand, are entirely different. They are lightweight. They are virtual calculations.
A measure takes up absolutely zero space in your data model's memory. It is just a stored formula.
It sits there, inert, until it is actively queried by a user interacting with a dashboard.
When the user drops that measure onto a visual, the DAX engine dynamically calculates the result on the fly, entirely within the specific filter context the user has selected.
And then the data vanishes from memory when the visual is closed.
It is brilliant.
But I have to push back here. I have to challenge this absolute rule. If measures are so vastly superior, if they are so incredibly lightweight and fast, and calculated columns are memory-hogging encyclopedias.
Why do calculated columns even exist in the platform?
Right. Why hasn't Microsoft just deprecated them entirely? Is there an edge case where a calculated column is actually the right tool for the job?
What's fascinating here is that there's a very specific architectural requirement for calculated columns. A virtual measure cannot be used to physically slice or categorize data. If the business stakeholders explicitly need to use a newly calculated categorization as an interactive slicer on the dashboard, for example, evaluating a customer's lifetime spend and categorizing them into high value, medium value, and low value tiers.
And then using those tiers as a drop-down filter to slice a map visual.
Exactly. That categorical data must physically exist in the Vertipack dictionary.
Because a measure evaluates dynamically after the filters are applied, it cannot be the filter itself. A measure cannot populate a slicer visual.
Exactly. In that highly specific edge case, where the mathematical output must be used as a dimensional filter, a calculated column is mandatory. But for any mathematical aggregation, sums, averages, ratios, running totals, measures are the absolute rule.
That is a critical distinction for the enterprise mindset. But when we are writing those virtual DAX measures, the blueprint to mastery demands advanced techniques to cut processing time.
Because a poorly written measure can still bottleneck the CPU.
Technique #1 in our blueprint, DAX variables.
Utilizing the VR and return statements within your DAX code is an absolute game changer for query evaluation plans.
Instead of forcing the DAX engine to calculate the exact same complex subexpression multiple times within a single massive formula, You use a variable.
Let's say you are calculating a variance percentage. You need the total sales, and you need to divide it by the total sales from the previous year.
In amateur DAX, developers will write the calculate function for previous year's sales twice. Once in the numerator to find the difference, and once in the denominator to find the percentage.
Which forces the engine to scan the entire data set and evaluate that complex time intelligence filter twice.
By using variables, you calculate the previous year's sales once, store the scalar result in a VR named prior year sales, and then simply refer to that variable in your final return division.
It drastically cuts processing time by halving the engine's workload, and it makes the code vastly more readable for future maintenance.
Technique number 2 is measure branching. This is about code governance.
Instead of writing one monstrous 1,000-line DAX formula with nested if statements that no one but you can decode, you build complex calculations like a tree.
You create a very simple base measure, say just a sum of sales amount, and call it total revenue. Then you branch off that to create total revenue year to date using the dates ITD function.
And you branch off that to create revenue YTD versus last year.
If the underlying core logic ever needs to change, say the company changes how it defines revenue by excluding certain tax codes, you only update that single base measure.
Because the entire tree is branched from that root, every downstream complex calculation updates automatically and flawlessly. It is all about maintainability and efficiency.
And speaking of efficiency, the masterclass blueprint specifically warns against using certain iterative functions unless absolutely necessary. The most notorious of these is the search function in DAX.
Yes. Search is one of the costliest functions available because it fundamentally breaks the advantages of the columnar database. It is an iterative function.
It forces the Vertipack engine to abandon its highly optimized dictionary compression and literally scan the data row by row, looking for a partial string match within a text column.
It is the enemy of zero latency. If you were running a search function across 100 million rows of product descriptions inside a DAX measure, your dashboard is going to freeze.
The enterprise architect avoids search in DAX at all costs. Instead, they push that logic upstream.
If you need to flag every product that contains the word refurbished, you do not do that in DAX. You replace it by generating a simple Boolean true or false column way back at the database layer or during the mQuery folding phase.
By pushing that logic upstream, the Vertipack engine only has to read a highly compressed, dictionary-encoded true or false flag, rather than performing complex string manipulation at runtime.
And similarly, we must ruthlessly avoid filter redundancy. If you have complex, multi-layered filter logic that defines what constitutes an active customer, do not write that massive DAX filter into 50 different measures.
Use stored procedures or data views to create a single source of truth upstream. Minimize the logical complexity required when deploying filters within the in-memory model.
Okay, let's take a deep breath because we have covered immense architectural ground.
We really have. We now have a zero latency, perfectly modeled, high-performance reporting engine. We have mastered the separation of M and DAX. We understand Vertipack compression and star schemas.
We have balanced our storage modes with aggregations, and we have deployed an optimized DAX blueprint.
But, and this is the massive pivot of this masterclass, standard reporting is, by definition, passive.
It is looking in the rearview mirror.
Oh.
You are just reporting the news.
Exactly. Enterprise architects don't just report the news, they automate the business response. Which brings us to our final major topic, beyond reporting, proactive workflows with Power Automate.
This is the paradigm shift. This is where we move from manual, human-driven analysis to automated, proactive business intelligence strategies.
The Power BI platform does not exist in a vacuum. It is tightly integrated into the broader Microsoft Power Platform, which includes Power Apps, Power Automate, and Power Virtual Agents.
This is where the deep dive transitions from data modeling to workflow automation. The platform utilizes over 300 native API data connectors and the Dataverse repository to perform prescriptive and cognitive analytics.
It stops being just a dashboard that people look at and starts becoming an operational nervous system that takes action.
Let's look at a highly specific, real-world case study of advanced integration. Imagine you are managing a global supply chain and you have built an incredibly precise DAX measure that tracks real-time supply chain variances.
In a passive legacy reporting setup, a regional manager has to physically log in, wait for the dashboard to load, visually notice that the variance metric has dropped into the red zone.
Open their email client and manually type out an email to the procurement department to address the shortfall.
The latency between the data indicating a problem and the human taking action could be hours or days.
But with Power Automate, Integrated directly into the semantic model, you build an active trigger. You establish a rule that says, if this specific DAX measure for supply chain variance drops below a 95% efficiency threshold, the system autonomously intervenes.
The workflow triggers instantaneously. Through the REST API connectors, it automatically fires an alert.
It updates an external Excel tracking table on a SharePoint drive. It generates a prescriptive, dynamically filtered PDF report detailing exactly which shipping routes are failing.
And finally, it sends an actionable adaptive card directly into a Microsoft Teams channel, tagging the relevant department head with a pre-configured button that says, Approve Emergency Reorder.
Now, I have to stop and really challenge this because this feels like we are crossing a massive ethical and operational line.
It definitely pushes boundaries.
We are moving entirely out of the safe sandbox of business intelligence and crossing over into live business operations. We are talking about connecting a DAX measure directly to an API that can execute external commands.
Are traditional data analysts really ready to have their dashboards actually execute real-world workflows that spend company money, alter supply chains, or trigger automated vendor emails?
What if the data model has a flaw? Are we just giving the dashboard a corporate credit card and letting it run wild?
That is the ultimate question of operational maturity in this space, and the answer is they have to be ready. This is the inevitable evolution of the industry.
As the sources state, knowledge is most valuable when it is understood and applied. The architect's job is no longer just to ensure the data is mathematically accurate.
The architect's job is to implement the exact governance and security guardrails necessary so that the data does not just sit idly in a dashboard, but actively and safely drives the business forward based on cognitive inferential patterns.
You use service principles, you use rigid approval workflows within the automation, but you do not shy away from the integration.
It is an incredible vision for what enterprise data can be. It is terrifying, but it is the future. So as we move into our outro, let's briefly recap this Cortex Lab masterclass journey we have been on.
We started by tearing down the amateur reliance on flat spreadsheets and established the strict enterprise architect mindset.
We explored the battleground of separating M for static transformation and DAX for dynamic analysis.
We covered mastering the Star Schema, ruthlessly managing high cardinality to protect the Vertipack dictionary compression, and applying the KISS principle to prune our models.
We navigated the complex trade-offs of storage modes, leveraging composite models and aggregations to defeat the network latency of direct query.
We unlocked the DAX blueprint to mastery, prioritizing lightweight virtual measures over physically bloated calculated columns.
Utilizing variables for query plan optimization and avoiding costly row-by-row iterations like the search function.
And finally, we integrated Power Automate APIs to evolve from passive reporting to building a living, proactive data ecosystem.
But an enterprise ecosystem is nothing without trust, which brings us to the very final step of the lifecycle: governance.
Using pro or premium capacity services, an enterprise architect must secure, partition, and validate the data. This means configuring incremental refresh policies.
And let's be precise about what that means. Incremental refresh isn't just the toggle switch. It requires setting up strict range start and range end parameters in Power Query.
These aren't just arbitrary dates. They are specific parameters that the Power BI service uses to dynamically partition your massive fact tables via the XMLA endpoint.
It dynamically rewrites the folded SQL query so that instead of reloading 10 years of history every night, the system only queries the underlying database for the last 3 days of changed data.
It drops the scheduled refresh time from 4 hours to 4 minutes. It is about control, efficiency, and massive scale.
And it means using endorsements, marking a heavily audited, perfectly optimized semantic model as promoted or certified within the cloud service.
This signals to the entire organization that this specific data model is the absolute single source of truth, effectively preventing the chaos of dueling spreadsheets and conflicting departmental metrics.
Which brings us to our final provocative thought for you to take away. We started this masterclass talking about the foundations of a skyscraper, the structural integrity of your enterprise architecture.
So, take a hard, uncompromising look at your current data models. Open them up tomorrow morning. Look at the data lineage.
Are they passive, fragile historical records full of redundant text columns, high cardinality keys, and physical bloat? Are they weighing down your servers, breaking query folding, and frustrating your users with endless loading spinners?
Or are they lightweight, highly optimized automated engines proactively driving your business forward through intelligent workflows?
Ask yourself this. If your data platform disappeared tomorrow, would your company just lose a nice reporting tool, or would its entire operational nervous system shut down?
Challenge yourself to build the latter. Build the foundation that can hold 100 stories.
Thank you for joining us on this deep dive.